Like I mentioned there, right? G's is one of our one of the big users of Apex. So they're using. So they have created a platform for IoT, industrial IoT. So they have, as you know, G is all over the world. They have multiple business units, and people buy their equipment. They're a 100-year-old company. So all this equipment that's in the field, whether it's like things in the like oil refinery in deep sea or aeronautical engines, they all have sensors, and these sensors generate a lot of data, right? And earlier they used to just save the data locally and do the processing later, right? And they kind of have been evolving, and now they have actually a cloud platform where this data gets streamed in, right? And they are enabling more and more of these devices to be able to send the data as soon as it's being generated. So they are putting the agents right on these devices or in on those locations in the customer, so that they can stream the data into the cloud, and then all the analytics happens in the cloud, right? So that platform is called Predix. It's a fairly unique platform because it's an industrial IoT platform. And one of the main first components in this platform is actually a time series ingestion application that's receiving this data, at high speed and a lot of data. And its job is to basically make sure that check for the sanity of the data, perform some basic analytics, and store it so that later on some kind of if they want to do machine learning and those kinds of things, they can do it. But if they want to do anything on the streaming side, any analytics, they'll do this on using Apex basically. So here's a brief agenda. I'll give you an overview of the G platform, then the specific time series application and how Apex was used, and some of the journey and learning. So this project was jointly, the time series part was jointly undertaken by our company DataTorrent and G. So we have actually engineers. We may have some engineers in this room. Oh, they left. Who actually worked on it. I was one of the ones, and then there are G engineers as well who are not here today, but I would like to acknowledge their role as well. Predix platform. It's a platform for cloud platform for industrial internet. It's based on Cloud Foundry. It provides a rich set of services for basically rapid development and processing of this IoT data, and basically runs in a managed secure infrastructure. And it also is a marketplace for different kinds of services. So any software vendor can provide a service on top of the G Predix platform, which their end customers can use. So this is to show that what kind of data that we're dealing with. It's not IoT data from your phone or something like that, right? It's not consumer grade things, right? It's not your thermostat or your lights or those kinds of smart information. It's actually information from windmills or like train locomotive wheels or like a plane engine and things like that. It's very critical data. They can't lose this data as it's coming in. They have to record everything. They cannot have wrong results, wrong calculations, because critical things depend on the analytics. So here's the Predix architecture. What happens is on the client side, on the client devices, there is what they call a Predix machine that's installed. The Predix machine collects the data from the sensors and then sends it over the cloud. And on the cloud side, they have the Predix deployment, and they to build their services, they have a microservices architecture, and to support the microservices architecture, they use Cloud Foundry underneath, and then basically they deploy all their services on top of that. And these services perform different analytics, and then they store the results and make them available to the different industries that consume it, and there are a bunch of applications that get enabled on top of it as well. So I'll go specifically into time series because that's the one that we are familiar with. So we are not experts on Predix because that's the G thing. We enable the time series application, right? So this picture is showing you data that's actually, so each line is like a sensor reading. So imagine a sensor is actually, let's say it's a temperature of a sensor. So it's maybe measuring this temperature every half a second, right? So it generates one line of event every half a second, and then basically these events are coming all the way to the cloud. They get batched up a little bit and then sent for efficiency. And it's a typical, like an engine may have thousands of sensors, right? So basically this is happening across every sensor. When this data comes in, what Predix can do is it can ingest all this data and efficiently store it. It can index it for quick retrieval and basically provide you all those nice features. And the main thing for them is that they should not drop any data. And the other thing is they also want to be able to apply rules. So for example, you may want to get suppose that maybe the threshold temperature is 93. If the temperature crosses 93, you want to get an alert because that something is wrong, right? So they need to be able to apply these kinds of rules on the data as it's streaming in, right? They can't store it and process it later, then it's too late. Right? So this is the specific time series architecture. So like I mentioned, there are Predix machines that are sitting on the customer side, sending data. The data comes and it gets processed by a gateway, which is a high-speed, it's a very efficient server. That's a network server that's written to handle high-speed data coming in. And then this gets put into a distributed message bus. And then from here on, they have an Apex application that's processing this data and then storing the results into stores. And once you have the result in store, then they can enable all kinds of applications like machine learning or any other applications that other vendors can provide on this store. So this is the critical piece. So they can't lose the data in this path, because once it gets stored here, then it's a store, right? It's available. And also they provide, once the data is stored, they provide APIs to query the data. They provide REST APIs. So for example, here this query, in this query you're asking for all the, I guess all the windmills in a farm in California, I guess, for their speed. So that's this query, and you're saying give me 1,000 results. So they provide this kind of functionality on the result data. So since you've already seen the Apex talk, I will just quickly gloss over it. So Apex is a in-memory stream processing platform. So it's you can basically write any kind of application you want on top of it, and it's built to process a lot of data coming in really fast. And this is basically the Apex technology stack. So we run on top of Hadoop, and on top of it we have the Apex engine, and on top of Apex engine would be your application. So you write your application with using something called operators. You basically build these operators and you connect them. You can use operators from the library, or you can basically write your own, and then it basically runs on the Hadoop cluster. So here's an example of an application that you could build. So this has actually 5 operators, 5 stages. So this first stage is actually reading data, could be from the message bus, and the second stage is filtering data. So here you may for example get some data which has some anomalous value, and you just want to drop it. You can drop it, or if it's like a bad format or something like that. And let's say then you want to calculate the top 10. So maybe you want to calculate the top 10 sensor values within the last minute. So you can write an operator to do that. And here we have split the job into 2 pipelines so that we can handle higher amount of data. And so if each of these pipelines give you 2 top 10s, you still need to take the results and calculate the final top 10. So you can write what's called the unifiers that to be able to do that. And then finally you're taking the output, and you might wish to store it in some data store. This is just to give you an example of how an application would look like. Okay, so these are the different operators that are available to you out of the library. You can of course write one from scratch anytime. So we have, if you have databases where you have data, we have operators to read from there, NoSQL, file systems, of course, Kafka and other streaming systems. And then we also provide some high-level high-level operators that do some sophisticated logic like deduping. So if you have data coming in and you need to remove duplicates, and let's say it's a long time period, right? You may get, let's say you need to look like a week back and drop a data even if you received something like 5 days ago. So that means a lot of data need to be efficiently stored in memory and so on. So we provide operators that can do that. And to build an application, there are different ways to build your application. So the easiest way, or the basic way, is actually you take each operator and you connect them up. So that's what we call compositional. But there are other ways to build an application as well. High-level API is one example where you are actually you don't know what are the underlying operators, but you define a series of transformations on a piece of data. So why Apex was chosen by GE was for two reasons: for both for ease in development of their application, time series application, as well as for operations. So on the development side, it's because it's highly performant and it's distributed, right? So you can fully use all the computing resources available in your Hadoop cluster. Second, it supports dynamic scaling, so you don't have to use up the entire, you don't have to provision for your worst case, right? You don't have to create an application that's just waiting there and doing nothing. You can, it can easily start with just one instance or one partition of every piece of your logic, and as more data is coming in, it can split and it can create multiple processes on the fly to handle new data. And then it's a rich set of operator library, so you can build your applications fairly quickly. You don't have to write everything from scratch. And finally, it supports exactly once processing. So what's exactly once processing? So let's say you have been processing data and there's a failure in your Hadoop cluster. Some node went down. What do, right? So what we guarantee is that you will not lose any data. You will not have any wrong computations, and if you're storing data in some external store, you won't end up you won't lose any data or store any duplicates, right? A lot of it is automatic, I should say, but there's a small piece of it that happens in the operators as well, and we have operators in a library that handle that. And on the operation side, first of all, it's purely Hadoop native. It just runs on top of Hadoop. There's no other piece of software that's required. Like I mentioned, it's fault tolerant, so the ops person doesn't have to do anything, mostly nothing. So even if there's a node outage or something like that, the application will recover automatically. So that's a good thing, right? And then it has ease of deployment. You can and the operability, which and we have a console where you can actually see all parts of your application, how they're performing, their metrics. You can even record the data at different points in your application. And of course we support the enterprise grade security. So if you have LDAP, Active Directory, or any kind of authentication, if your Hadoop cluster has Kerberos, so all that will work out of the box. So here's the time series DAG. This is the actual application that they built. They have some proprietary logic that they don't want to share. So this is part of the DAG. So this operator is actually fetching data from Kafka, from a streaming source like Kafka, and this operator is actually parsing the data. So this is JSON data that's coming in. It's being parsed, and once it's being parsed, if there's any bad records, they go to this error operator, and this error operator basically logs the data in some store so that they can go back later and see what's going on, what's wrong with the data. And if the data is fine, it basically goes into this time series sync, which will eventually write it out to some store, and further processing can happen there. And then they basically also calculate metrics of, for example, how much data has been processed and per customer, so that they can bill them later. And all the billing metrics are all sent to this operator, which actually sends it to a billing system, right? And we also, I think this is slightly difficult to see, but actually this is a modification of this application. So we also ended up building this application. And this application, what it does is, the first part is the same. This part is the same here. But what we're also doing is we added this piece, which is actually applying rules on the data that's coming in, right? So you want to basically get alerted if a particular sensor value is greater than a threshold, right? Or the difference between two successive values is greater than a threshold. So individual value is fine, but so that means you cannot lose any piece of data, right? Then otherwise the difference is wrong. And or if you don't receive a sensor value for the last 2 minutes, think about that, right? They want to get an alert. So all those kinds of rules, we've actually built out in this DAG. Okay. Okay. So scaling, I talked about the different scaling options. So each stage of your logic can actually run in multiple processes, so it can process more data. And dynamic scaling as well. So you can so for example, let's say initially you start out like this. Stage 1 and stage 2 have 2 partitions each. Now let's say you start getting more data. Then maybe stage 1 can handle it because it's doing very light processing. But stage 2 may be doing heavy processing, and it cannot handle this large amount of data, the speed at which it's coming in. So if you just leave it at 2 partitions, eventually what will happen is it will not be able to process data at the speed at which it's coming in, and then the data will get blocked, and eventually it will end up blocking the downstream client, right? We don't want that. So what will happen is, as soon as the system starts seeing that there's more flow, it will automatically create 2 more partitions. So we just had 2A, 2B. Now we have 4 processes, and now each of them are processing 1/4 versus half, right? So they can handle the higher data rate. And then once this happens, maybe stage 3 also needs to be partitioned, and that will also happen. And so this is the same application with all the partitions, right? Earlier what I showed you was the functional view of the application, just the different business logic. But actually you can see there's like multiple partitions, right, of each stage. So because they're processing millions of events per second, right? So you can see that this is the whole operator tree, right? So there are actually 8 input partitions reading data from Kafka, and there's like 8 partitions here that's doing the parsing. So all this view this is our monitoring console. It's showing you everything, right? And for each of them, you can like zoom in and see how much data is processing per second, what's the latency. You can even record the data, right? So you get so it's not like a black box for you. So some of the development aspects, the Kafka operator, I'm just going to briefly touch on a few of them. Our Kafka operator is dynamically scalable. It can create. So this is the Kafka message bus. So the Kafka message bus itself supports multiple partitions. So it can receive it can basically receive data over multiple processes. So on the Apex side too, we can actually read parallelly from these processes, and it happens automatically. And we provide different ways for you to say, let's say you're building this application, right? And you want to, as you're developing it, you may need to test it. Right, so but if there are problems, how do you debug it, right? So we provide a whole bunch of tools for it. So first of all, we provide something called local mode, so where you can run the same application as is right on your computer, even without deploying onto Hadoop. So you can test it, and you can debug in your Java IDE or whatever you're using. You can put breakpoints, you can do that. Then we provide a detailed log mechanism, so you can see all the logs of every container, every partition, and you can view them. You can even search, do a limited search through them. Okay, I need to hurry up because of time. So this is another view of our monitoring console. So here it's showing you the stats, the overall latency, the amount of data processed, and here it's giving you the stats per operator. Right, and this is just a demo application. So this total application is using 28 GB of memory across all the processes. So some of the challenges we faced, some of it was around restarting, and so they wanted to be able to basically stop an application and start it later on, and they wanted it to continue exactly from where the previous application stopped, and they wanted to do it in a way that even if they change their application code, they want to be able to do that, right? So we basically did some engineering there to be able to. So one of the things is when you restart, you want to go and start reading data from the old checkpoint, right? So from the old Kafka offset. So we are basically storing this offset externally in Zookeeper so that we are able to do that. And there were a few issues and so on that were fixed. They also, for example, for the rules, they needed to be able to store a lot of data in memory. So we actually built a very efficient storage mechanism that's a combination of an in-memory and HDFS backend storage system, so that they're able to store large amounts of data in memory for their rules engine. Okay. Some of the key takeaways: the system was tolerant to failure. Upgradability was important, and we achieved that. The logging and events were very useful, as G told us. They went with dynamic partitioning because static partitioning is limited. I mean, they found it limiting because they want to be able to scale up and down dynamically. And yeah, it's some of their takeaways. Don't keep testing periodically on the cluster. So do some amount of development and then deploy it, give it a try, and then once you find the bugs, you go back, fix your code, and redo it. Just some common good practices. And we also provided them a performance testing and benchmarking tool. So actually, you can take the same application and run it with different configurations, so different number of partitions, different memory sizes, and then it can basically tell you how much data it can process with each configuration. So that way, they can plan their cluster out. So if today they're getting 1 million events and tomorrow they're going to get 100 million events, they have a rough idea of how much hardware they would need. Yes, some Q&A, and I also wanted to acknowledge my G counterpart, Venkatesh, who's not here. But I can take any questions that you have.